And then there's the partial derivative of alpha. Oh, I see. And then there's the partial derivative of beta. And then I add them and calculate some more and calculate some more. And oh, there you go. So this is the the exterior derivative of that one form works out to im over 2r cubed zxy. If you look at this, this is the flux form of xyz. So you're looking at the vector field xyz divided by r cubed. This is the Coulomb field. This is actually the formula for the Coulomb field written as a two form. But there's an I, there's an M for magnetic charge, and there you go. So that's the proof that that potential one form at the start was the so the exterior derivative of this monstrosity up here, right? This function, when you exterior differentiate it, it gives us the formula for the magnetic monopole. The exterior derivative of this one form naturally then gives us the field strength of a magnetic monopole. The question is, where is this not defined? Where is this potential form not defined? That's the Dirac string. Can you guys tell me? Z equals to R. What is that? That's the z-axis. The z-axis is the standard Dirac string to this potential. So you can take this same formula, and you could take that Dirac string and like rotate it any different which way, and that would still exterior differentiate to the same thing with the artifact of not being defined along that rotated axis. In spherical coordinates, it's prettier. Here it is. In spherical coordinates, here's the potential. It's just Im over 2, 1 plus cosine theta d phi. All right. And again, we have the Dirac string along theta equals to 0. Fun fact, we're in physics. Theta is phi. Theta equal to 0 is the z-axis. I know. Fun, isn't it? So you could it's the positive z-axis too, by the way, because r is the square root of x squared plus y squared plus z squared, positive square root. So you could also look at, so let's see here, this would be, I called this up here a sub south, because it's defined on the whole southern hemisphere of space. It's the southern potential. Whereas if you did minus that, then that would fail to be defined actually on, that would be defined on the north, and the Dirac string is on the southern, the z negative axis. So if you take both of these together, you covered the top half of the sphere, you've covered the lower half of the sphere at arbitrary radius. I mean, you got everything. But you need both of these potentials together to cover all the space. And the way they're related, if you look at their difference, they're related by Im d phi. You might recognize this from the principal fiber bundles. When we took the difference of two connections, we got something in the differential of the gauge group. Yeah. So that's the relation. And so what that speaks to is that the principal fiber bundle that underlies magnetic monopole is, it's got some, it needs, you actually need two connection forms to cover the whole thing. There's some kind of non-trivial topology that you can't get around. There's an obstruction to writing down a global one form. So let's see here. This is section 9.11 in Nakahara, which is a great book. And so I think what I show in here, curses. trying to remember. Hopf meets Dirac. Transition functions that arise in the context of gauge transformations for the magnetic monopole was exponential of that. And if we just consider the formula north equal to south plus IM d phi, remember we proved that the north is the south it's the transition function plus the derivative of the north-south transition function. This is assuming that the mathematics of the monopole truly follows the principal fiber setup. Once we make the connection, we can verify the Hopf bundle is the magnetic monopole with charge m equals to 1. Let's connect the dots. So this is the north-south transition function. When you look at the mathematics of the Hopf bundle, it's the Z1, Z2 over Z1, which is this, which is that, which is that, which is that, which is that. So I've basically, in the pages I just kind of skipped over, I show that the Hopf bundle can be seen to produce a pair of connection forms which are related on their intersection in the same way that the north-south Dirac string potentials are related. And so we identify that, in fact, if you had a magnetic monopole, if you look at what that means at the level of fiber bundle, it means you have a Hopf bundle. So, I don't know, it's kind of, I don't know if it's interesting or not. I think it's a little bit interesting. It's something I only partially understand, really. This I know is that there's a deep asymmetry between electric and magnetic fields as they relate to space-time. Because we can find this global potential for electric fields. I mean, God has so arranged physics to allow us to understand it without that much sophistication. If we did have magnetic charges flowing and floating about, our understanding of voltage would be much more complicated. And you can start to see that in these equations. But the other interesting thing, of course, is that if, thought experiment, if there did one exist and you could study like Dirac's potential, you'd see that you're actually studying the same math as that of a principal fiber bundle, the Hopf bundle, which is described in more detail up here. It is what? What is the Hopf bundle? So I think it's just the bundle space is S3 and the Hopf map. So it's S3 with a base space of S2. So in some sense we're like freezing the radius in space-time and just studying what happens at a particular radius. You could think of it that way maybe. And this is the formula for the bundle map going from the 3-sphere to the 2-sphere like that. And then, that's of course that's the projection map. And to define the bundle, there's bundle space, you could use complex notation, super nice. Let's see here. There's charts on the Hopf bundle. When you define charts, these are nice charts, but they have trouble when z equals to 1, which corresponds to the North Pole, singular at the North Pole. Of course, you can do I think +1, then you lose z equals -1, which is the South Pole. So you get the North Pole, you get the South Pole charts, and you can work out the relation between the charts. And I don't know, I'm not probably showing you enough to make sense of it at the moment, but anyway, fun fact, there is a interesting and non-trivial relation between magnetic monopoles and S3 as a bundle over S2. Yeah. I guess, yeah.
Yeah, I've heard of something like homotopy of S2. There's a Hopf map that runs from S3 to non-trivial.
Mm-hmm.
So this turns out when the homotopy group of S2 is non-trivial.
The homotopy group of S2 is non-trivial. Yeah. The third homotopy group. Yes. So these same calculations getting in tune with those calculations is part of what's involved with understanding those results. Because this is an important example for bundle topology and stuff. But anyway, when I worked that out and I saw that it was the same equations as the magnetic monopole when you get into it, it was deeply satisfying when I first worked it out for myself. And more details and more physics can be found in Nakahara's book, which is now in its second edition, which I do not have, sadly. But the first edition is super cheap and also good. All right, well, Monday, back to the A calculus. So did that wet your whistle? Was that, okay, that was physicsy enough? All right, good. Pretty physicsy.